welcome everyone. And today we have the pleasure to receive Dinis Álvares, who did the master in Instituto de Técnico in Lisbon, and he will present the work done there. So feel free to ask questions during the seminar. There will be also time at the end. And also Dinis is looking for PhD thesis opportunities. So if you have any information or suggestions about this, also can. So we think he will be here for lunch as well, and yeah. So you have the floor. Thanks for being here.
Thank you, João, and thank you for having invited me as well. And before I start the seminar, I'd like to say something about the moment when I decided to go through gravitation. So I'm originally from the north of Portugal, really near me, so really Braga, almost, Spain. And at some point I went to Braga to live while I was in my 9th grade. And this was around 2016, 2015. And the House of Science in Braga had just opened. And they were inviting people to talk there. The first person was Márcio Ferreira, who is a big person in astronomy here in Portugal, for those who don't know him. And on the 17th of November, 2017, I was, still a bit unsure what I wanted to do. I just moved places while I was very young. I didn't know exactly what. I had met a guy from the University of Minho, Antonio Novo, and he's particle physics. But then I got him interested in gravitational waves because, he's a physicist, he knows about black holes, right? And then there was a talk about black holes in the House of Science. And I went because, I was interested, it seemed cool. I enjoyed Márcio Ferreira, and then there were two people, right? One was Pedro Cunha, and the other one was Carlos Ferreira. And that was basically the moment when I said, okay, this is what I want to do. Okay.
Big responsibility.
So after many years, coming back now here is a great pleasure for me. Yeah. I'm saying this because sometimes, when we're doing science communication, sometimes it might feel like we're speaking to the void, right? We're speaking to hundreds of people, or a dozen, or just one or two, and sometimes it feels like, no feedback sometimes, but one of them will hear you, and at some point will be here one day. So thank you. Thanks. So yeah, now about what I've done, and I'm also going to speak a bit of what I'm doing now in the end, but I still don't have a lot of details. But I will speak to you about what I did in my master's thesis, which actually went pretty well. Okay, so I did this work with Alex Frango-Vignales and other Gasparin Garcia, in Centro Técnico, although right now I'm part of the Institute de Telecomunicações, which doesn't have any official connection with black holes, because it's about telecommunications, but I'm working with George Rocha, who is a part of it. Very well. So this work that I did with Alex, is this working? Oops, sorry. Yeah. Okay, yeah. So this work that I did with Alex and Edgar, I'll first guide you through hyperlocal slices, why are they useful. Then I'll speak about the EZKs, the regular initial data. So this is just a test for you to be, let's say, sure that this is working. Then we'll go to Schwarzschild, the charged case, of course, and you'll see the positional modes and the decay that this gives us, which must match some theoretical predictions if everything goes fine, and then the conclusion. So, introduction. Why did I start working on this, and why are hyperboloidal slices relevant? Okay, because they allow us to reach functional infinity. And functional infinity is where we mathematically define gravitational waves. So they have, it's a very interesting region to, explore. And there are ways that people usually do this. So let's first go to the Penrose diagram. We have the Cauchy slices, right? Tau t equals constant. They are represented by the green lines here, and they reach I0, which is spatial infinity, and they'll never reach at any point one of these two parts of the Penrose diagram, right? Which are future and past nil infinity. The ways people have found to reach these parts, especially, I'm going to only focus on functional infinity, right? The people have found a way to numerically evolve data to reach that part of the Penrose diagram is something called Cauchy characteristic evolution, which is one of the ways people do it. And if you were to represent this in the Penrose diagram, essentially you cut these slices at some point as a cylinder, and then you match them onto an array and evolve the data of that cylinder until it reaches functional infinity. Okay. There's also another way, which is Cauchy characteristic matching, which is kind of similar, but you basically construct the slice artisanally. This is CCE and CCM, and the way you represent this is basically construct this such a way that it's continuous at least to the second order usual. But it has a problem, of course, and so Cauchy characteristic evolution, as you were seeing, has a problem of usually the cylinder is kept at a finite radius, and then you have to extend it more or less, and depending on how much the radius is big or how bigger it is, your results might be affected or not due to that. I'm talking about, for example, by scattering, sometimes can lead to some not reasonable results in your data. So hyperlocal slices come in here because they are actually a way to reach functional infinity in a continuous way, a differentiable way actually. And you can, for example, just do it by defining a new time coordinate. So you have the t tilde, and then you have a height function which basically lifts the Cauchy slices. You can imagine that as if it's lifting the Cauchy slices as it reaches functional infinity, and then voila, you get these slices which reach this part of the Penrose diagram. Now, one of the questions that people usually do, and actually Miguel Leão, who was the jury of my master thesis, did me a question that I didn't know how to answer, and then I did the calculations afterwards. Because it's due to the fact, if you see this here, you might ask, okay, why do the slices, hyperbola slices, reach functional infinity in a way which is not similar to null rays, right? Null rays would be at a 45 degree, but you can see here, you basically have something which goes horizontally. And this is quite strange, right? And so the question that he did at the time was, what's the angle at which hyperbola slices actually reach functional infinity? And then, if you look, for example, if this KCMC, I forgot to mention something. So this specific height function in this case gives you constant mean curvature slices. Okay, so this doesn't need to be constant mean curvature. It can be whatever you want. In this case, this is the function that comes up automatically when you do the calculations. So, for example, David Illich and other people like to do this function by hand, and they have some properties which are kind of free. They only have to match some criteria, which I will not talk about it here. If you increase this KCMC in value, you see that for the same values of tau, which is the new hyperbolic time coordinate, you see that as the KCMC drops, they go faster, which means that actually the opposite is happening. So this one actually is going faster. This everything makes sense, right? The higher KCMC, the faster your slices evolve. If you were to switch your hyperboloidal height function, you can also reach the functional infinity, and there has been some work you can actually match past null infinity to future null infinity in a way with this type of matching between the two height functions. So about Leão's question, what's the angle at which hyperbolic surfaces reach functional infinity? This was actually something that Luciano also asked me at some point. And so I did the calculations, right? We have the Penrose diagram. These are the coordinates. This is Minkowski, okay? The hyperlocal slice, you just change the t tilde to tau and the other function. And then when you calculate this quantity here, right? So I decided, okay, I'm going to calculate the derivative. And then the final result, as r goes to infinity, you are basically you're asymptotically approaching functional infinity, and you get this answer here. And the idea is basically you can have the hyperlocal slices can go from being a null ray to horizontal, and then they again become a null ray. So that's what happens in the if this is interesting or not. And actually, the flat slices are given for this specific condition in this specific hyperlocal foliation. So we can speak a bit more about this, about the implications of this after. So what has been done in hyperpolarized slices? I've given you a bit of what they do, what has been done. So this was an idea from Jörg Frauenlieder, who is now in New Zealand now, and I mean, he has been there for a long time. And so he did this back in 1980s. And in the meantime, you had several people, one of them, Alex Álvares, which was the main supervisor. And he and Sasha Husa, they developed a lot of the problems with gauge conditions, right? So we have the gauge conditions for usual GR, etc., the usual slices, but then when hyperpolarized slices come in, gauge conditions have to be adapted, because then you are also taking into account the fact that you have future null affinity, and it's an ingoing null surface. So it was strange that until this point, these gauge conditions with hyperpolarized slices are still not really well understood, but they work, and but they are not perfect. Okay. And actually, this is the problem with going to 3D right now, right? So hyperpolarized slices, if the idea is to extract gravitational wave data at some point, then 3D good gauge conditions is the thing that's lacking right now. Okay. So yeah, the real scalar field has been done in spherical symmetry. A young Niels field as well by Anil Zanginoglu. So he was one of the main proponents of hyperpolarized slices, and he actually was one of the people who brought Alex into this. All in spherical symmetry, and as I was telling you, 3D is in progress right now by David Illich, Christian Peterson, and Alex as well in another stuff, and Edgar, and some other people, of course. So what we are doing here, so the idea in this work was, okay, we are finally going to have the electromagnetic interaction to be modeled on hyperpolarized slices. Okay, I had already the scalar field before, the real scalar field, and we wanted to try to model the charge scalar field, which is like a natural extension to the real scalar field. But of course, it adds the Maxwell equations. So this is done by solidifying the scalar field, and you then have to change, of course, the covariant derivative. You have the invariant with the four potential, and that's basically it. And why are we doing this as well? It's, why Reich and Nordstrom? It's in the limit case when it's supercharged. It can also be used as a toy model for Kerr, although it's always in spherical symmetry, right? Of course, Kerr is 2D, but here it's only spherical symmetry. So the Einstein-Maxwell-Klein-Gordon system, it's a big name. And of course, we have to take into account the coupling to Einstein field equations. So our stress energy tensor is given by a part due to the Faraday tensor and electromagnetic interaction, and then the part of the scalar field. Well, the star here is just a complex conjugate. Okay. Maxwell's equations. Now, when we do this, I actually have an error in my thesis, which Miguel didn't see, which was due to these two small, symbols here, the nu and mu. They actually have to be in this order for the correct sign to be right, because the Faraday tensor is antisymmetric, and I had mu. And after I had shown this for a lot of people, nobody had noticed it. And then on the last, the second paper regarding this project, only one referee said, okay, I only have just one comment. The sign is wrong. And I was like, you're right. So yeah, this J, so the four currents, this is due to another charge related to the charge scalar field. And this is given by this equation here. Sorry. So now the important thing is, how do we put the hyperpolarized slices in a numerical setup? Okay. So the first thing we want to do is rescale the radial coordinate. All right. So the radial coordinate goes to 0 to infinity. We want it to go to 0 to a number. Okay. In this case, 1, which is the easiest choice. We do that with this first conformal factor. Okay. We'll have a lot of conformal factors, unfortunately. And this is omega bar. Okay. Then we do another conformal transformation, because when you do this first one, your metric now becomes divergent, because the terms that are proportional to R now have something which goes to 0, which is due to the conformal factor. Okay, so now we have to regularize the metric such that this effect does not destroy our numerical setup. Okay, so this is the new conformal factor, and you'll see that this omega and the omega bar have to be coordinated such that they match exactly when they are reaching infinity, 0, divided by 0, but then it doesn't give something wrong. Okay. After we do that, we go to the 3+1 decomposition. So right now we are already in the position that our metric can describe a hyperbola slice. We do the 3+1 decomposition. We have the gamma, which is in this metric, the normal vector to the hypersurfaces. And we go then into the BSSN Z4, which is a common formulation for evolving, the Einstein field equations. We do that by introducing another formal factor, which is the usual, right? So this is the usual one, which people already know, which is the chi factor. And this now gives us finally the gamma, which is, the thing that we're actually going to evolve. And we're going to also evolve this conformal factor, okay? So the final line element is the usual one. You have the lapse alpha, you have the beta, the shifts. In terms of NR, this is standard as well. And of course, again, spherical symmetry in this case. So I've given you the setup, what are hyperbola slices, how we put them in the code. I'm not going to go into detail, of course. Tell me.
Yeah. So just on the slide before you were saying BSS and Z4, but there's a difference, right? Do you use V4 or BSS?
I have both. I have both of them, basically. So what I do, BSSN it actually comes after Z4 in this case. So I first add the terms in the Einstein field equations. So I add the Z quantities there, and then I decompose them, etc. And then I use the things that come from BSSN into that. Okay. So these also affect. So it's like a hybrid thing, because also the Z4 quantities, some are affected by the BSSN formulation as well. So it's a bit in the mix. Yeah, but I use both of them. Yeah. Awesome. Okay, so the first test we're gonna do is a regular initial data. Okay. So when I mean regular initial data, I mean Minkowski, and then we have a perturbation to it. So the first thing we should do is divide the scalar field into the real and imaginary parts. We also do the same for the derivative. We also do the same for the vector potential, and this phi is somewhat similar to the electric potential, but it's not exactly actually this is one of the things in GR, which is a bit something hard to understand in the beginning, and then the vector potential. And the initial perturbations we pick the real part of the scalar field. We could do that with imaginary parts as well, but we decided with the real one, it's indifferent. And then the radial part of the vector potential, we also do some Gaussian perturbation of it, okay? I should have to say, because one of the things that you might be questioning yourself is, why am I evolving the radial part of the vector potential if I'm using spherical symmetry, right? Because in spherical symmetry, you don't have a magnetic field, right? So why would you care? But actually, the evolution of this quantity affects the electric potential, which affects the electric field. So actually, you have to evolve this radial part, even though physically you probably wouldn't be expecting. So the last thing, of course, we are doing constraint evolutions. So this is a free hyperbola evolution, but this is a constraint, okay? So we solve the momentum constraint by this simple condition, and the Hamiltonian constraint has to be solved numerically for chi. Okay. So chi is such that we have conformal initial data. So what you see here, so the chi, the conformal factor from the SSN, this is 1, so it's not exactly 1, right? It's a bit changed because we have this perturbation. It would be 1 if we were in Minkowski. Okay. Then the electric field initially is 0. I'm not plotting the other quantities because otherwise it would be too much. And then this red part here is the scalar field. I'm multiplying it by 10, and just so we can have everything in the same picture. On the right, you have the modulus of the scalar field. So this is also taking into account the imaginary part, and this is the Wissner-Sharp mass of what you're seeing. And by the way, yeah, don't forget, right now this one is functional infinity. Okay. So when we put this playing, you see some part of it goes out at functional infinity, then we have some reflection back here in the origin, and then everything goes out at functional infinity, and everything is fine, right? So we are using outwards, so only outwards going conditions on the setup at functional infinity. Okay. So this is interesting. Of course, if we make the amplitude big enough, we should at some point expect that the scalar field will form black hole. And now you see that the amplitude is much higher. It seems similar, but notice that now it's not multiplied by 10. So actually we're, 10 times bigger. And chi, you can see now the deformation in chi. And when you put this playing again, now it's a bit slower in the beginning. You have some twitching there. And at some points you have an apparent horizon finding an apparent horizon. You have alpha going to 0, you have chi going to 0 as well, and you have all of the indications that a black hole was formed. Okay? Of course, you cannot say this a priori, but you have all of the indications that a black hole was formed. So actually, you can also do that, and you see that not only a black hole was formed, but that the Horizon Nordstrom one was formed, right? So because you have an electric field here active. Okay. Tell me.
Yeah, sorry. Alpha was the last, right?
No, sorry. Alpha is less. Yeah.
It's not going to one. That's
At functional infinity. That has to do. Yeah, that has to do a bit with. So in collapse simulations, they are a bit crazy sometimes. But it doesn't go to one, and this is due to the fact. I mean, I think no, I'm not really sure about this, right? But it cannot be one because you also want the points going in according to the functional infinity position. So it's an ingoing surface. So you actually want to bring the points a bit inwards, and the lapse has to be according. I don't know honestly how to.
but
Yeah.
so you're saying it's more. Is it related to the hyperboloidal slice, to the collapse, or both?
Tell me, sorry again.
You were saying it's like in the collapse situation, but is it more due to this physical system, or is it more due to the hyperboloidal slice?
I would say it's more due to the hyperboloidal slice. Yeah. Yeah, that's the best I can tell you. Yeah, honestly, I spent a bit of wondering about the gauge conditions. So this is roughly. I have some things in the afters, like the backup slides, right? But this is a 1 plus log with some gamma freezing in the shifts as well. It's not really. Yeah, I cannot tell you for sure.
And is this why it's hard to find gauge conditions in 3D? That's
What I've gathered. So people in New Zealand have been trying to also put things in 3D, but they use a different gauge, which is called the Gauss gauge. But they have the problem, which is as the time goes on, they actually see smaller and smaller region of space-time, which is bad, right? Because at some point we want to see how things are in the future. But I think the problem is trying to fix the position of scribe. I think that's the problem right now. But again, I cannot tell you it's exactly this because I think nobody really knows exactly what it is, But yeah, it was the York founder who he came to do a seminar in Central at some point, and he told us that. Yeah. So yeah.
Thanks.
Yeah. So tell me.
I have a
Yeah.
curiosity, maybe a very naive one, but why does the outgoing pulse go so fast getting to null infinity, whereas the ingoing one seems to go so slowly to
The origin, right?
yeah.
I think that has to do major with the conformal factor that we're using. So, but I cannot say for sure though. I cannot say for sure why it goes so fast. It seems to go too fast almost.
Because it goes to infinity, right?
It goes to infinity, exactly. Yeah.
But could it be that it's because of your slides that indeed goes to functional infinity? Like you have a lot of distance and time to travel, right? In a way for a given spacing, while in the middle is more the usual, slicing. So it's more what we expect. I would say, but the other one is like, okay, it has to seems to be super loopy. Yeah.
Yeah, exactly. That's also one of the things that I've gathered some people to work around this, but I think it's not superluminal because the hyperwall slices should not allow this. And also, it's one of the problems. For example, if you wanted to simulate a massive scalar field in this, some people have tried it. It gives problems because you are forcing things to behave to go to functional infinity. And if you have a massive scalar field, they can't, right? So we have some energy breaking conditions at some point here. In this case, we don't, right? Because this is not massive. But yeah, I don't know exactly what's the explanation for that is.
Couldn't be also due to the labs because it's getting smaller and smaller as it gets closer to the black hole and further away it's still okay. It's bigger, so time would go on faster.
I see your point. Yeah,
Way.
yeah. Could be. Yeah.
You have a scalar field which is charged but not massless.
Yeah. So it's not. It could not be a boson star, for example. Yeah.
Do you think that's okay? Something which is charged but not massive,
If that's okay.
physically speaking.
No, yeah. Physically speaking, I wouldn't say that's okay. Yeah. But what's your? Yeah, I mean,
You have charge traveling at the speed of light.
yeah, like I have a light ray basically almost. Right?
But it's charged,
But it's
electrically charged.
Yeah. No, I mean, of course, physically, it's not the most relevant thing, right? It's
No, I understand.
Yeah.
You're on with this. It's fine.
yeah. But I mean, like one of the ideas that I was discussing with Alex is actually trying to put the massive scalar field here, but with an appropriate mass function.
Well, certainly standard model, all particles that have electric charge, they have this.
Yeah. So yeah, I think this would be, but it's hard to, I cannot tell you for sure because I think nobody really knows how to put a massive thing here. But for example, I spoke again with Leon because he also had some papers on the charge scalar field at some point, a massive one. But again, he uses usually the Einstein toolkit and the other stuff which use the first method that I was describing here. So yeah. Okay, so let's go to Schwarzschild. But I know that some people will do it at some point. I know Christian Peterson at least when he's working around it, the problem. So yeah, let's go to Schwarzschild. But Schwarzschild, when we are using hyperbolic slices, you cannot do the same thing in the beginning as we were doing for Minkowski. So you can't just propose a tell. Technical problem. The technical problem is that hyperbolic slices do go to functional infinity, and it was some other student before me who tried to evolve the massive scalar field in hyperbolic slices. This was with David Illich, and they were getting at some point like something not working well at functional infinity, right? So
This is the usual problem, right, of having a wave, but then you're trying to describe longer separations between points with the same wavelength. It will not work.
yeah.
I mean, that's just a guess.
No, yeah.
Something that's problem, but maybe that would be.
Yeah, but for example, modeling a massive charge scalar field when the mass function, it's always the value of the mass that we give it, and if as you are approaching functional infinity, you force the mass function to go to zero. Could also be a possibility. This I have discussed with Miguel. Actually, it was a suggestion from Miguel. You seem to have some dots count.
Well, you mean by mass function putting a term in the Lagrangian
Yeah.
with an M of R,
Mhm.
but then you impose it. You don't give any dynamics to that. You just impose
Exactly.
level.
Exactly. Yeah.
Well, in that sense, perhaps you could do something like instead, you could calculate the curvature space. It's asymptotically flat.
Mhm.
You could get a mass function.
Mhm.
The equations are a bit more complicated.
Yeah. That's why I still have
But the model will be self-contained. It wouldn't require an arbitrary profile.
Okay, I see your point. Okay.
That's a non-minimal calculator.
Yeah. Okay, so anybody has any other questions? Okay, so yeah, let's try to build hyperbolized slices in Schwarzschild. Let me see. Okay. And when you impose again that you want constant mean curvature slices, in this case, of course, this is not the only choice. You have this condition for the height function, where A is just the usual one, depending on the type of black hole you're choosing. Okay. This CCFC is important because this is a integration constant, and that, well, I said this doesn't seem important, but actually you have to choose it very correctly, such that your slices start. I mean, they actually don't seem to start anywhere, right? But they go from functional infinity until the I plus, let's say, of the white hole. Okay, so they actually never reach this R equals R0. So this is like the minimum distance at which the hyperbolized slices can be, but they nonetheless go through the horizon. Okay. Yeah, this is how basically they evolve. I'll show you in the end when you actually evolve this with the lefts and the shift. It's basically similar, but it's more faithful. If you choose a bit, like just a bit off. When I say a bit off, I mean like 0.000001 off. Then your slices start going into the event horizon, and they reach this point R till equals R0, and they stop being continuous, right? So at some point you have the jump, and they continue in the inside, but now it's completely. There you have a jump. It's discontinuous, so you have a problem. Okay, so this is very important when doing this type of slices. Putting this information now into the numerical setup that I was showing you before. Now your chi goes to 0 initially, your alpha goes to 0 as well. This is expected. And I again do perturbation on the scalar field, and the electric field now it's going to be very, very small because the perturbation is always very small, such that it's 10 to the 14. Okay, so this is now close to the double precision that I was using. So you're first going to see a bit of jump radiation on the electric field part in the beginning, but then it continues. Okay. So yeah, you have that problem there. If you use long double precision, that doesn't happen. This was the one that I was doing with double precision. And you see that it goes very, very slowly as it approaches the black hole, let's say. And it becomes ever more slower as it approaches, because now what you have to imagine is that you're not actually going to the black hole, right? This region here, it's going infinitely far away to the I plus of the black hole, okay? And then it becomes, due to the numerical, because like the size and the distances there are so big, actually you start to have imprecisions, and that's why as they approach here, they start to be a bit spiky, etc. But now this only happens inside the event horizon, and yeah. So what you see here is that the incoming charge scalar field now transforms the black hole into a charged black hole as well. Okay.
But you said it only happens inside the event horizon. You mean the event or the apparent?
Sorry, the event horizon. Yeah.
I was wondering if you were tracing the event.
I'm going to show it in India how we did that as well. Yeah.
Can I ask a question? So when this pulse goes inside the event horizon, shouldn't the event horizon size kind of slightly increase?
It increases, but it's so small that you don't see it here. But it decreases. Yeah. The reason why you don't see it's because it's very small. So what you're seeing here is 1,000 times smaller, and and what more? And if the too big perturbation in this case, the gauge conditions and the Z4 sometimes get crazy, so you have to keep it small in this case. Tell me.
It also seems that there's a steady pulse going inwards, but because of the curvature of space-time, you should have scattering at every point. So some of these pulses, there should be some outgoing. Is there, we just don't see it?
Yeah, well, I think we just don't see it. Yeah, exactly. I think that's the reason.
Very small.
Yeah, it's very, very small one. Yeah, but
Actually, going back to Carl's question from earlier, because here it's going to the other side, but very slowly.
it's very, very
On
slow.
the right, it's
Super
really
fast.
right? So
Yeah, I mean, I think that's, yeah. But it is your question then?
yeah, I mean,
Okay.
yeah,
Yeah.
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 Yeah, sorry, I guess it was maybe more.
No, but I agree that the question is important to answer. I've talked with Alex and Anil and some other people, and it's just probably again it's the same quantum velocity, but yeah. So when we now look at the charge case, of course, we first have to solve the Gauss constraint in vacuum. This is a simple solution. Charge of R squared, that's what we're used to, and then multiply by chi to the 3/2. And in this case, this factor is important because it makes the electric field go to 0 at the origin and not go to infinity, which would be very awful for numeric. Okay. And if we are to do some perturbation in the scalar field, we also have to solve numerically for the extra electric field that this charge density is creating. Okay. So again, this is 0.6 charge black hole, so 0.6 the mass. And you can see that the electric field now is much bigger, okay? But nonetheless, it goes to 0 at the origin as it's supposed to. Okay, so this is the electric field. We do a perturbation nonetheless. And now I'm plotting also the electric potential, and the vector potential as well. Okay, just so that you see some other quantities how they evolve, although these, of course, are gauge quantities, okay? So now you have the imaginary part, which is this this white thing as well. Now you see the interaction between both. The phi actually changes quite a lot, which wasn't supposed to, which wasn't expected. And you see here, for example, how both the real and imaginary parts interact. And at some point they go inside the planet horizon and they behave similarly to what we had before. Okay. So yeah, nothing quite new here.
Sorry,
Tell
what was phi?
Phi is, so it's the electric potential,
Okay.
but it's not because it's the electric potential multiplied by the labs.
Okay, I was just confused because I was wondering it was like
The scalar field or
yeah.
Sorry.
It's negative, so.
So yeah. No, I mean it's a lot of variables. Actually, I'm evolving 17 at the same time. So, but I'm not showing because yeah. Okay. So if you want to see how the slices evolve, and actually this is how we reconstructed the event horizon here because we did a collapse simulation, and then you see at some point where they meet, and then we drew basically where the slices go to. So you see, so this is like the real evolution of a hyperbolic slice in a collapse simulation. And you see how they evolve. At some point, they disconnect from the left and they go up into I plus. Okay. On the right, you just have the trumpet relaxation. So this is Schwarzschild with nothing in it. And it's very similar to what we were seeing before. And again, you see it disconnects from the left at some point. This is due to the numerical imprecision, let's say, on the left, because it's going to infinity as well in that case. So now we can focus more on the scientific parts that you can extract from all these simulations. Okay, Fascinal mode ringing. I think most of you have heard of it. If we put the real scalar field interacting with the Schwarzschild black hole, we get this. So at scribe in this case. Okay, and if we were to do the Cowling approximation, which is basically not involving the Einstein part, just the Klein-Gordon part, okay? You see it's a bit different, so they overall agree, but then as time progresses, they are a bit different, okay? we do a fit of the fundamental mode, which is in this case we should only have the fundamental mode because it's spherical symmetry. It's not the best, but I've compared this to other fittings as well, and this seems to be according or in agreement with all of the fittings that have been done to this mode in hyperboloidal slices. If we try to do the same for the Russian Nordstrom case, interacting with the charged field, scalar field, you see that the amount of oscillations that you get, it's actually really, really small. You only have one oscillation and that's it. And this makes it very hard to actually, fit any frequencies. There's a paper from Emanuele Alberti that he tries to calculate the frequencies, but you cannot fit it with only one half oscillation. Okay. This is, of course, due to the nature of charge, the interaction between the scalar field and the black hole.
Are you considering the scalar field and the black hole charge to be the same sign, opposite sign?
It doesn't. It didn't. I tried both, and
It didn't matter.
it didn't matter. Yeah.
But I would expect that, say, you start with a pulse with the same charge, black hole, and if you increase a lot of H coupling, this should be noticeable in the dynamics. Even you would have that the pulse would move outwards rather than inwards in an extreme case.
That's true. So you see a difference in the dynamics, but in terms of this late time behavior, it seems very
Because it absorbs and it rings.
exactly. Yeah. Yeah. So the late time behavior of a scalar field, the Richard Price at some point, he has a famous paper, and he said, okay, at I plus, you expect the scalar field at some point to decay with time to the -3, and at scry, time to the -2. Late time behavior with the charge scalar field, it's a bit different. I think I'm going over time, right? No, okay, that's fine. It's a bit different. You have this beta factor, and this beta factor is a bit more, complicated, but it has to do with the charge coupling, let's say, between the charge scalar field and the charge black hole. And you see something interesting happens when this reaches, this quantity here is equal to 0, right? So this beta becomes 1/2. So you have like some cutoff at some point, which is due to the fact that you are passing now from purely gravitational decay to electromagnetic decay. Okay. So yeah, these are quantities that were done by Shahar Hov. Again, late time scalar field. So now we see, if we let the simulation go a bit further, the decay as it's supposed to, and as we go to the inwards of the slice, you see that the decay becomes stronger and stronger, which is expected, right? Because at scry, it decays slower. And as you go to the inwards of the slice, which as time progresses, you can think of it as going to I plus, you should have something which decays faster, okay? And actually, if you plot the quantities, if you do this numerical calculation, basically what you get is the exponent of the decay, okay? So in scry, you have the decay going to -2, which is this blue line here. This is expected. And as you go to the inwards of the slice, this approaches -3, which again is what we were expecting, okay? If we do the same thing for the charged case, now you see that the decay is slower, and this is due to the electromagnetic interaction. But nonetheless, this doesn't mean that the real and imaginary parts are, they have stopped. They continue oscillating with a very precise frequency. Okay, and if you plot this for several charged coupling, let's say, you see that as it increases, it becomes slower and slower, and at some point, for example, the extremal case, you have something which matches with, for example, 0.6. Okay, which was what we were expecting. Now, this graph here, I would say this is one of the main results in this case. So this is a graph that tells you basically the passing from 0 into electromagnetic interaction as you tune it up a bit, and then you go to the extremal case. Okay, and this gives you the exponent with which the charge scalar field is decaying. Okay, so each triangle is a simulation, and you increase the QQ and you get the P, which is the exponent, okay? So for 0, you get -2. As you increase the charge coupling, you start to have a behavior similar to this blue line, which is due to Shahar, etc., and Piran as well. So this was a calculation by Canoplia. It was so most of the results in the tail decay are they seem to say it should be something like this, but nonetheless this is the correct result, and it's correct. I mean the one which your simulations agree with more. But not what the interesting thing here is that you can construct any type of decay, let's say, which is somewhere between this minus 2.0 and this minus 1.0 if you tune the charge coupling properly. Okay, I mean I didn't do that because each simulation takes like 10 hours, 12 hours, and the point at some point was done, right, in terms of how they agree with the previous calculations. And you can also do the same thing for I+. So this is not exactly I+. As I was telling, this is that approximation that is, if you go to the inside of the slice and you let it go long enough, you can do the approximation that you're almost as if you were in I+. And actually, so this was something that I was expecting to work, and it actually seemed to agree. And you see something very similar to the above plot, but for I+.
Yeah,
Tell me.
so you're varying this coupling capital Q times small q, right?
Yeah.
But what are you doing for the charge to mass ratio of the black hole, capital Q2?
Okay, so what's changing in this case was, so the mass was fixed, one in this case. The charge of the scalar field was fixed as well, and I was changing the charge of the black hole. Yeah, so actually the charge to mass ratio was changing of the black hole.
But are you getting to externality?
Yeah.
So you have no problems in simulating this in an extreme black hole?
I mean I have to tune a bit. To get extremal I have to tune some values in the beginning, but it's actually there's an instability which is Alex wasn't expecting that actually. I don't know if it was something that I did in the equations or whatever, because I had some problems with the electromagnetic part that I had to fix by hand, let's say. And this is not due to the extremal case, this was in general. And it worked. Yeah, and it's constraint solving as well, so it's, If, as I was showing you before, if even though the modulus of the scalar field is decaying with the exponent that you're seeing in this left plot, nonetheless the real and imaginary parts continue to oscillate. That's what we were seeing with very precise frequency. So I decided to do the Fourier transform to see how the frequency changes with the charge coupling as well. And actually, the Shahar part, their paper, they also predicted this frequency, and you can see it in white. And so, this peak here is due to that beta, when they turn to zero, the formula that we were seeing before. So basically, when this goes to zero, and then at some point becomes imaginary, then your frequency suddenly starts to change according to that function there, okay? So what we see here is actually something that disagrees with their result. Actually, the frequency with which the things oscillate continues to increase. It has like a divided by 10 factor, but overall it's a linear increase. So conclusion, I was gonna tell you a bit of what I'm doing now. So this was the previous work, the work I'm doing now with George, because probably some people have some idea about this, but since I'm already a bit late in time, I'm just gonna tell you in words what I'm doing. It's basically, so this is not related to this. We're doing thin shells in the only known rotating solution in Einstein-Gauss-Bonnet, and we're trying to see how the shell evolves. So if somebody is interested in discussing that, I'll be happy to discuss. So let me just show you, what comes after what I've shown you. As we were saying, the massive charge scalar field is the next step, or interesting step. Of course, going to 2D before going to full 3D could also be interesting. This way, we could also add the magnetic field interaction. And of course, the final goal, it will be always to do 3D simulations, okay? So this would be the thing that I wanted to talk to you about, but no problem. And in summary, we have the Einstein-Maxwell-Klein-Borda system for the first time involved in hyperbolic slices, the collapse as well of a charged scalar field into a charged black hole. the initial data as well for a Russian raster black hole and parallel slices has been developed or found, let's say, and yeah, the transition between curvature to electromagnetic-induced tails, which was something that was studied, let's say, in a systematic way, was shown at least, some first results in this case, and the extracted frequency doesn't agree with the predictions that were done before by Sharon and Solid Piran, and that's all that I have to tell you. Thank you so much.
Thanks a lot for the presentation and keeping right on time despite the many questions. So we have time for more, if there are any questions. Yes, please.
Thank you very much. So in the charged black hole for the charged scalar field, we can have super radius, so your pulse will be amplified. If you find any evidence for that, or because your pulse is composed of many frequencies. And there could be frequencies in the super radiant version.
Okay, yeah,
Actually,
actually,
spectral analysis of that sort, such that you could see if some frequencies were indeed amplified or not.
that's actually interesting. What I found, but this was only for the external case. But yeah, but I haven't tried to. I didn't think about that actually, but that's an interesting question. Yeah, that's interesting. Thank you for that. Yeah.
More questions? Are there questions online? So I have one actually, but so something that I was not sure I understood well about the constraints.
Yeah.
So you mentioned them for the initial data.
Yes.
Okay.
Yeah.
But then in the evolution, are you solving them or it's just the Z4?
Z4, yeah. Z4, yeah. But I mean, I have the. Yeah, I mean, I can show you the graphs at some points of. Yeah, so. Yeah, you see that they overall they converge appropriately. Yeah, we are using a Runge-Kutta for everything, so fourth order. Yeah. The problem, for example, when you do so this is for for the collapse, there's a problem that happens inside the apparent horizon, like the quantities do not converge appropriately inside the I don't know exactly why. I mean, but I mean, I know why. I mean, it's a collapse, right? It's a collapse. It's a very intense simulation to simulate. But the important thing is that throughout then the rest of the, the numerical points, it converges, and most importantly, at scry, right? Because that's the idea of hyperlink slices. Yeah.
Do you have any constraint damping in the evolution for the electromagnetic field?
That's a good question. Yeah, I don't know if I showed it before. Yeah, okay, it's here. So it's basically this quantity here, this psi that I have to use. This was, I took it out from a Carlos Bona book on magnetohydrodynamics. There's another way to do this, which is similar to that for. I know, for example, Jorge Patiño in the expositor in Lisbon uses that. But yeah, this worked fine. I have some problems because you see that this is multiplied by the metric, right? And at some point, I have this guy here multiplied by the conformal factor, which goes to 0 at functional infinity. So the thing that I was getting was not convergence at functional infinity because, the constraint solving part was not taking into play at functional infinity. And I was like, I spent like 1 month or 2 months trying to understand it. And then I changed by hand, right? I took out the conformal factor. That was multiplying by this guy, and then suddenly I got conversion. Yeah, so it was actually one of those moments where I was like, wow, that's crazy.
Actually, I don't remember the point exactly, but a few months ago there was a presentation by Daniela Kors, and he was also mentioning something like this. So it was not the same system exactly, right? But it was the GHG system, I think, and she had some labs multiplying the constraint damping.
Yeah, exactly. That kind of stuff. Exactly. Yeah. Sometimes you have to change the constraint damping a bit just so big things numerically can work. Yeah. I mean, you can actually see, right, the conformal factor here. This is what happens, right? This was the first equations here while I was preparing, but then at some point I just take out the omega. Because the idea is just, okay, if the psi is positive or negative, I want it to evolve in the other part. So, I mean, if it's multiplying by a positive quantity or not, fine, right? Yeah.
Yeah.
Any other?
More questions? No? Then let's thank our speaker again.